Welcome. At the end of this video, you're going to have a decent idea of what we mean by signals and systems. What is a signal and what is a system? Because it's really not that clear, actually. In fact, as you'll see, the title, Signals and Systems, is kept general on purpose. So let's kind of understand why that is. So, first of all, let's start with kind of a thought exercise. Imagine being inside an auditorium and listening to your favorite singer. And let's take away all of the electronics. Okay, no electronics, no microphone, no PA system. And let's say you're on stage. Your ear is right next to the singer's mouth as he or she sings a song. Think about what you hear. Okay, think about whatever performance you like. Okay, now let's rewind that and suppose that the singer sings it in exactly the same way, except you are now sitting in the middle, in a seat in the middle of this auditorium. Think about what you hear now and how it is different than the first rundown of this. Okay, and if you'd like to pause the video, you can certainly, but I'm gonna give you some ideas of what you experience the second time around. How is it different than the first time? And the first one is obvious, I would hope, and that would be a decrease in volume. A decrease in volume. Because as the signal travels, or as the I shouldn't even say signal yet, as the singer's voice travels, then its energy actually gets attenuated by things inside the room. Okay, seats, other people, and just friction. Anyway, there's also a time delay. The speed of sound is finite. So it takes some time for that singer's voice to reach you, especially if the auditorium is bigger. You can really observe that effect. Okay, there are echoes. So there's not just one path, okay, that reaches you. The singer's voice will bounce off walls and so forth, and then reach you at different times, each with its own volume. So each echo will have a certain time delay, and each echo will have its own volume. And that's interesting. Okay, now the next one, and the last one that I'm going to give you, it depends on your maybe your knowledge of music, but pitch and frequency are kind of the same thing. And I'm going to just comment that there will be frequency. I'll just write changes for now. Changes. Frequencies and pitch are the same thing. So you might find that lower frequencies reach you with a certain volume, and higher frequencies might reach you with a different volume. So those frequencies kind of they change. Their properties change. This is why if your roommate is in the next room playing some music, then you can hear the bass frequencies, the low frequencies, more easily than the higher frequencies, because the bass frequencies are harder to attenuate. So these frequencies, they all have their different echoes. They all have their different time delays. They reach you in different ways. They all have their differences in volumes, actually. All right, in this situation, we would say that the singer's voice is a signal. We'd say that's a signal. Okay, and the room, the auditorium, drawn here as this black box, is the system. And the singer's voice, the original voice, so what you heard when your ears were right next to his or her mouth, we would say that's the input to the system. And then the system, or the auditorium, shapes that signal with these kinds of properties. Decreases and changes in volume, changes in delays, echoes, changes in frequencies. Okay, and then what you hear in the middle of the auditorium, okay, is also a signal. What you hear. In this case, we would say the singer's voice is the input, and what you hear is the output. Okay? And this particular example, this is an acoustical system. In our course, we keep things at a very high level, general level, signals and systems, because what we learn in our course can be applied to acoustical systems, electrical systems, mechanical systems, and so on. This is not a circuits course. We don't do circuit analysis or anything in this course. We keep our types of analysis highly mathematical so that they can be applied to any sort of, a lot of different, actually, applications. Okay, so the singer's voice, so we can measure the singer's voice with something that's sensitive in pressure. So if we did that, we can make a plot. Whoop. Control Z. We can make a plot of the pressure versus time, and it might look something like this. Okay, something like this, and I'm gonna label this X, parentheses T, like this. Okay, so that any point in time, I can read off my graph, and I have a value for X, the pressure, right? This might be in decibels. And this different value of T here, I can read off, and I have a different value of X in decibels. It doesn't have to be like that, though. I can have maybe a different system. Maybe we can look at the voltage across a capacitor as it charges. So that looks something like this. So I'm going to call this now X of T. And this is T. This is the X is the voltage now across a capacitor, and as it charges with respect to time. Okay, I could have a tuning fork. This would be a mechanical system. Tuning fork. All right, in a tuning, so the tuning fork is its own system, like this, and what makes up that system is what makes up the tuning fork. So, the specific materials that go into making the tuning fork, its shape, its specific shape, all of that goes into this box. And then let's say we were to strike the tuning fork. So we would give it an input that would look like this. Maybe this is time. We would just give it a quick strike like this. And then what would happen to the tuning fork's output? So if we measured the position of one of the prongs, we would expect to see something like this. X of T. T. So you can see there will be some vibration there. So the position of a mass spring system, or the position of a mechanical system, can also be a signal. All right, I'm going to give you a different type of signal here. We have yet to really define these yet, but let's say I looked at the price the closing price of the Dow Jones on a daily basis. So maybe today it closes at this price, and maybe tomorrow it closes at this price, and so on. So we have these daily closing prices. This seems to be a little bit different than those other signals, right? Because the first several signals that I gave you, we could plug in any value of time and we can read off what the signal is equal to. Here, and here I'm using n, I can only plug in integer values of n. I can ask, relative to some reference point, what's the daily, how did the Dow Jones close today? How did it close tomorrow? And so on. But I'm not allowed to ask in between. Certainly the Dow Jones has a value in between those, but I'm looking at the daily closing price. So it does not have a closing price between 2 days. So it's actually, if I asked what is x at 1.5, it's not zero, not zero. It's undefined. Okay, undefined. It's actually not even allowed. We're not even going to ask what is the signal at 1.5. That does not make sense in this case. But over here for the continuous case, right? I can ask, what's the value of the capacitor voltage at 1.5 seconds? Certainly. Okay, so there is a difference here between these two signals, and this type of signal here, this is called a discrete signal, and almost always our independent variable is going to be time in our course. So we're going to call this a discrete time signal. Okay, this is a discrete time signal, and I'm going to use the notation like this. More on that in a second. So x square bracket n square bracket. And these first several signals that I've drawn here, these are continuous. Continuous because the value of the independent variable time forms a continuum, so I can plug in any value I want there. And so because most of our signals we're going to look at has an independent variable of time, we're going to call this continuous time signal. And again, we're using this notation here, x parentheses t. So the way that we set up our notation is going to signify to you, are we dealing with continuous signals with parentheses and t, or are we dealing with discrete time signals with square brackets and n? You see, because there is that fundamental difference that you cannot plug in just any old value into n, but you can plug in any old value in for t. I actually want to give you another example of a discrete time signal, one that's a little bit different. Any sort of display, a television, a monitor, cell phone, has an array of pixels. Okay, and these pixels form, they're discretely located. There's nothing in between the pixels. The pixel value tells you what color, tells your computer what color to make that pixel. Okay, so this is actually a two-dimensional signal where we can talk about this way and we can talk about this way. And so you give me a coordinate one way and the other way, you give me a coordinate, then I will tell you how high, what value our signal is there. So this is a two-dimensional signal. These were all one-dimensional back here. And not only is this a two-dimensional discrete signal, but the independent variable here, or independent variables, are not time, they're space. So, we go horizontally and we go vertically. Still, we would just call this discrete time signal. So almost always the signals are time. And so time is just kind of a catch-all, it turns out. So even pixels in a grid, we would still call this a discrete time signal, even though the independent variables here are space. Okay, we're actually not going to look at too much in this course, two-dimensional signals. We're going to stick to these guys, one-dimensional signals here. How does our signal change with one variable, not with two? Now, what we do in this course is actually to look at both continuous and discrete kind of interchangeably. Everything we do for continuous, we're going to do for discrete and vice versa, because it's very important both that we analyze both of these guys, because continuous signals are what we would say naturally occurring. Continuous signals naturally occur. The sound pressure as somebody speaks, the voltage across a capacitor, a mechanical system vibrating, mechanical body vibrating. These are naturally occurring. They're going to be continuous time. On the other hand, things that are man-made usually tend to be discrete time, man-made. Especially things that occur in computer systems. Computers are always discrete because they have a finite memory and a finite hard drive. So they have to be discrete. They cannot store every single infinite value demanded by a continuous signal. They can only store discrete points. And so everything in a computer is discrete time. What we usually end up doing is processing naturally occurring signals with computers. Therefore, we need to understand both continuous time and discrete time signals. All right, so you should have a decent idea now about what we mean by signal and what we mean by system. In the next video, we're going to start kind of describing some properties of our signals. Specifically, and we even kind of talked about it here, we're going to start with the energy and the power in a signal. This is related to the decrease in volume. What we would say is that the energy has been lost in the signal. So let's check it out.